thermodynamics is we've discussed before, but we've always kind of discussed it in terms of energy diagrams, where we look at the energy of maybe our reactants and compare that to our energy of our products, right? And then look at, for example, maybe the heat energy, delta H. And we said that delta H is always the delta whatever is always products minus reactants. All right. So this sort of discussion, quantifying this difference here, talking about the energy change in chemical reactions. This is what thermodynamics is. All right. And so it is something that we've gone over, although we might not have used the word thermodynamics specifically too much in the past. Okay. Again, delta X of whatever it is always final minus initial. All right. And we have worked with delta H before. We worked with delta T, change in temperature, before, right? We haven't really talked a lot about change in volume in terms of thermodynamics or change in pressure, and we won't still, but in general, it's always delta X is final minus initial. And this is a little bit of a review here, but we can calculate the delta H for this chemical reaction. Do you remember how to do that, Alyssa? How do we calculate the delta H for this chemical reaction given these delta HF values? It's okay if you don't remember, it's been a while, but what do you think?
Is it product minus reactant?
Yes, that's right. So specifically, what would I do? What would I put in my calculator?
So you do negatives. I mean, I guess you don't have to do the negatives. You can put that at the end, but negative 698.7 minus the negative, so it would be plus 393.5 minus negative 285.9.
Like that. Negative 19.3. And what is that telling us, a negative 19.3?
Because the delta H is a negative, it means that it's an exothermic reaction. Is that right?
Mm-hmm. That's right. Okay, very good. What does this delta HF mean? Do you remember, Sarah? What's the F mean?
Yeah, I think that's delta formation, maybe?
That's right. Delta H of formation. So we can identify the delta H of formation for any given compounds. It's essentially how much energy will be associated with forming these compounds, whatever the compound is, which contains bonds from the elements that are minimal in the amount of bonds that they contain. Very good. So 19.3 kilojoules here. Same thing, negative 315 minus the negative 92.3, negative 46.19. All of these are coefficients of 1, 1, 1, 1, 1, 1. So the delta H is, delta H of formation is just that value right there. But remember that the delta H of formation energies are per mole of material. So if these had coefficients, you'd have to multiply those values by those coefficients. Okay. So here's a table type of a setting. And if we are given this chemical reaction, let's just talk ourselves through this one, Alyssa, real quick. Again, we need to look at our table to find the delta H of formation for the products. Here I see magnesium chloride. Here's the delta H of formation. What about the water? What's special about the water in this table?
Gaseous form, so you have to use the negative 241.8.
All right, so state matters. Very good. So in my calculator, I have to take negative 641.8. Whoops, 0.8. Negative 641.8. I'm going to add that to my negative for the gaseous water, 241.8. Oh, what happened? Oh, negative 241.8. There we go. So I have a negative 883.6. And so that's my product side. And on the reactant side, what do I have to do, Sarah? What's kind of tricky about the reactant side here?
You just use 601.7 for the MDO. So
That's right. Plus what?
plus 2 HCl's, that'd be 2
Yeah.
times 92.3, or negative 92.
Very good. All right. Did I include all the appropriate things there? So now I have a negative 883. That's my products minus the reactants. So my answer should be a negative 97.3. Okay. Very good. So we had to pay attention to the state, and we had to pay attention to any coefficients indicating that there were more than just 1 mole of that material in the reaction. All right, good. We've talked about this before, that delta H is specifically the heat energy, but that there is also what we call work energy that is done by a chemical reaction. Now, work energy is usually done by the change in volume of the gases in a chemical reaction. So if a chemical reaction has its products that are more moles of gas, then we say that that reaction does work on the surroundings because it pushes the surroundings out of the way to have more moles of gas in the product side. If it has less moles of gas in the product side, then we say that the reaction has been worked on by the atmospheric pressure, right? It's made the reaction push down by that atmospheric pressure, okay? But the work energy and the heat energy can be combined into what we just call the total energy, or E. So delta H is usually just the heat energy, but E is all of the energy. So there's energy again in work, and there's energy in the heat that's gained or lost. And in any of those scenarios, the heat that's gained or lost is always going to be much more significant than the, well, not always, but it's typically, very typically, typical to have the heat energy much more significant, much larger than the amount of work energy done. But that's not always the case. So, here's an example of a chemical reaction in which we start our reactants with 6 moles of gas, but we end with 7 moles of gas. Okay? So, PV equals nRT, that's our new relationship that we can think about in terms of gas. The pressure stays the constant, the outside pressure is constant in this reaction, but we get a change in volume related to the change in moles of gas. So thus we can predict the work by this relationship. The change in moles of gas times RT, where R is 8.314 and T is our temperature in Kelvin. 8.314 in the units here are joules per mole Kelvin. We can, therefore, look at our moles of gas change, which here would be 7 minus 6, so 1. That would be our change in moles, 1, times our 8.314, times our temperature, and that would give us our work energy. Now, we throw in a negative sign. We throw in a negative sign because we want the work energy to have the same type of relationships in terms of positive or negative to the delta H the heat energy. Delta H, a negative sign, means the reaction releases energy. So if this is a positive number, products minus reactants, that would mean the reaction would release energy. And so we throw in a negative sign to make sure that our units are going to be negative. We just talked about this, but 8.314 is in units of joules. So the work energy that's done by the gas change in the moles of gas, will initially be in units of joules. So again, it's usually a smaller amount compared to the delta H. But the delta H, heat energy, and the work energy come together to form what we call the total energy, E. And that's what we see here. Total energy is our Q, our heat energy, and our work. And if we call our work component as this negative delta nRT, then the energy, delta E, is related to the delta H, those are the values that we were just finding, minus the delta nRT. So we can use the change in moles in the reaction times the RT, put a negative sign in front, add it to whatever our delta H is, and that will be the total energy for the reaction. Okay, so here it is. We have a chemical reaction. The following reaction, calculate the delta H and the delta E at this temperature. Now, temperature becomes important, not for the delta H so much, but for the delta E, because delta H plus the work energy is our delta E, and our work energy, again, is found by looking at the change in moles times R times the temperature. So, the delta H here, we have 6 moles of water. They told us that the delta H formation for water, negative 241.8 for gaseous water, negative 393.5 for carbon dioxide, 0 for nitrogen gas. It's elemental, and that's important because often in test questions they won't provide the delta H of formation for elemental materials, and people will be like, wait a second, I can't solve the problem because I don't have the information for the elemental material. But we always want to remember that in its elemental form, the delta H of formation is just 0. So if we take the products here, 6 times this, 12 times this, that's just what we were doing before, minus the reactants, 2 times this, 8 times this, right, I left out the 3 times this because it was 0. Products minus reactants, that is going to give us our delta H. Okay, so that's what we did before. Now, how do we find the work component? Because we need to add the work component to the delta H, and that will give us our delta E. Can you help me, Alyssa? What did we have to do to add the work component here?
I'm sorry, can you say that again?
How do we identify the energy that is either required or released in this reaction in form of the work energy? Not the delta H, the heat energy, but the work energy. What was it that we needed to do?
So you could use the delta H minus the change in moles times R times T.
Okay. So, what is our change in moles? What does that mean when we write work energy is equal to negative delta nRT? Where do we get our change in moles? What does that mean?
The moles of the reactants, the moles of the products.
In gaseous form, right? All right. So what does it look like? How many moles in the gaseous form on our product side?
21.
Okay, good. So we got 21 moles of gas on the product side, minus how many moles of gas on the reactant side?
10.
Is this one gaseous? Well, it's just 8, right?
Yeah. So it's 8. Sorry.
That's fine. Moles of gas. So 21 minus 8, 13 moles of gas times 8.314 times, what's our temperature, Sarah? What do we do for our temperature for this one?
25 degrees Celsius. Or, I just need to make that Kelvin.
And that's right. So that's 298.
Yeah.
298. 25 plus 273. So 13 is our change in moles. 8.314, 298. All right, so 13 times 8.314. Was that our R? Double checking here. Yeah, 8.314. Times our 298. Did I do that right? 32,208. I thought it would be less than the delta H. Did I do that right? Why did we get such a big number, Alyssa? It's kind of just a trick question to help us remember when we run into this problem in the test, the final. What are our units for this one down here? What are our units for the 8.314?
Joules.
It's joules. That's right. This is in units of joules, whereas this is in units of kilojoules. Okay? So if I want to add these together, I have to take my joules and divide by 1,000, and then I'm going to add it to my 13,898. Oh, I also have to remember that there was a negative sign here, so it's negative 32. So I'm going to multiply that by -1 just to get that negative sign in there, and then I'm going to add that to the negative 13,898.7. Okay, so the resulting energy, the total change in energy, is our 13,930, where again, the delta nRT only contributes relatively small amount of energy to the total process. Okay, very good. I don't want to spend all the time necessary for you guys to go through this by yourselves, but we had the answer. This is the same problem before. Let's see, right here. Here it is, right? Magnesium oxide, HCl, and we got negative 97.3. This one was looking for the delta H. So now we're doing it here, but this time we're looking for the delta E. So we know the answer is not A, right? But we can start with our 97.3. And our 97.3 is what, Sarah? What is our 97.3 for this reaction? Just a reminder. Remind everybody.
That was, I don't remember. Was it,
It's the, yeah, the enthalpy, which means the delta H. So this is the delta H, all right? And the delta H minus the change in moles times RT, that will give us the delta E. Okay, 500 Kelvin, so that's nice. It goes right there, 500 Kelvin. R, 8.314. Okay. Now, we should have one little tiny conversation about this 8.314 here. That's a constant, and it's the same R value, and we use PV equals nRT, PV equals nRT, where this R here had units of liter atmospheres per mole Kelvin, right? Whereas this R here has units of joules per mole Kelvin. Joules per mole Kelvin. So they're both called R's, and they'll both be provided for you somewhere in the exam. And the model for these questions we have are, they usually don't confuse you very much because each question has its own material. But generally, all of these equations are on one table, and so people have to be careful about which R they choose. But you can tell which R needs to be chosen simply by recognizing that we're looking for an energy, joules, or kilojoules, or whatever, and this has to equal to something in the form of energy. So that's going to be joules per mole, getting rid of the mole, that's the R value, right, per mole, and then per Kelvin for the temperature. All right, so there's our R, there's our temperature. What's the delta N for this reaction? I think Alyssa told us the last reaction is delta N. So Sarah, can you tell us the delta N for this reaction?
So I think it would be -1.
Yes, that's right, -1. Because on the right we have 1 mole of gaseous material, that's 1 mole of water. And on the left, we have 2 moles of gaseous material, just the 2 moles of HCl. So 1 minus the 2 is our -1. We still have to throw a negative sign in there for this. So meaning that in terms of releasing or absorbing energy from the surroundings, this reaction does not release work energy. It absorbs work energy. Absorbs work energy. What does it do in terms of heat energy, though, Alyssa? Does this reaction release or absorb heat energy?
The reaction as a whole, or just this part?
This reaction as a whole, does it release or absorb heat energy?
It releases heat energy?
Yeah. We can tell by the delta H the heat energy, and we just went over a little bit about how we know that in terms of work energy, it actually absorbs energy. All right. So let's see if we can find the delta E. I know that the delta E is going to be slightly less negative. Slightly less negative. I don't know how much. But essentially, I'm saying that it can't be C. It could be B or D. I guess I'd be surprised if it was B. But we can just find out, right? 8.314 times 500 times -1. 8.314 times 100 times -1. And then we're going to take our delta H and subtract that. So in a way, you multiply by -1 again. But 97.3, negative 97.3 minus, now do I want to subtract my -4157, or what do I have to do to that before I subtract it, Alyssa?
You have to turn it into kilojoules instead of joules, so it'll be minus -4.157.
All right. There we go. So we went down to 93.1. Okay, very good. So we took our delta H. Now we didn't just calculate the delta H again. We did that before, and so we were saving some time. But taking the delta H, and which is our heat energy, and then combining it with our work energy gives us our total energy. Okay, very good. So that's a good place to stop. Thermodynamics is a lot of fun. Lots of different things we can learn about energy of reactions. And, you know, this world, we need to figure out how to use energy more effectively, right? It's not a good idea to just simply say, stop using energy, because energy usage is related to the advancement of societies and the advancement of people, the growth, education, the abilities of people to contribute, all related to consumption of energy. So we can't say we're not going to consume any more energy. We want to be good stewards and use our energy appropriately, but the answer is not in conservation. It's a boon and it's a helping component, but we really need to find ways to make a lot more energy and consume more energy, because that's the way that struggling societies, struggling economies are going to grow, is by consuming more energy. And we need to understand these equations to do that. We need to understand these equations and how these equations relate to kind of what we're doing in the world today and what we want to do to move forward. Okay, so if there's any questions, you could ask me now. Otherwise, I will see you guys on, is today Wednesday? Friday. See you guys on Friday, right? And then we just have Friday and Monday, and hopefully we'll get through at least 2/3 of this, maybe the whole chapter, and then we'll have in our final, and we'll try to have the final open from Tuesday to Friday, I think. Probably open, maybe even Tuesday to Monday. Any questions?